Hello, I am Radhika Chanvarkar from MVP's KBT College of Engineering, Department of Computer Engineering. This video is based on the concept of sparse matrix. The objectives of this video is to understand the concept of sparse matrix, to understand the alternative representation, which is also called as the triplet representation of sparse matrix, and to study operations like simple transpose of sparse matrix. Now let's see, what do you mean by a sparse matrix? A matrix is defined in terms of rows and columns. If the matrix contains many zero elements and very few non-zero elements, then such a matrix is said to be a sparse matrix. A matrix is usually defined by its size m by n, where m represents the number of rows and n represents the number of columns. If a matrix of size m by n contains few non-zero elements, then there is wastage of space in storing the zero elements. Also, when the operations are performed on such matrix, the computations will also result into zero values because most of the operations will be performed with the zero elements. So, this leads to wastage of space and time. So, in case if we are having a sparse matrix in which there are only few non-zero elements and most of the elements are zero, then instead of storing it in the regular row by column form, they are being stored using an alternative representation. In the alternative representation of sparse matrix, only the non-zero elements are stored. Hence, the space requirement will be optimal, and also as the operations will be performed only on the non-zero elements, its time requirement will also be efficient. Now let's see what is the alternative representation of sparse matrix. As you know that every element in a matrix is assessed by specifying the row number and the column number. Hence, in the triplet representation, the non-zero elements are represented by their row value, column value, and the actual term value. So you have to store the row number, column number, and value in the triplet representation, which is again consisting up of only 3 columns, and the total number of rows are equal to the number of non-zero terms present in the matrix. The zeroth row in the triplet representation is being reserved to store the total number of rows, the total number of columns, and the number of non-zero terms. The triplet representation is ordered by row, and within the rows it is ordered by columns. So it is having a row measure format of representation. Now let's see an example of this. We are having an original matrix which consists of 7 rows and 6 columns. In this, you will be observing that most of the elements are zero and there are very few non-zero elements. So, this is a sparse matrix. Now, this sparse matrix will be stored in the triplet representation, which consists of only 3 columns. The first column stores the row number, the second column stores the column number, and the last column stores the term which is non-zero. As you know that in the triplet representation, the 0th row is reserved to store the total number of rows, the total number of columns, and the number of non-zero terms present, and from the first row the non-zero terms present in the original matrix are being stored in the row measure format. So you will be observing this non-zero term 3, which is at the location 0th row 0th column, will be stored as 0th row 0th column and the element 3. Then in the 0th row 3rd column you are having element 12, and in the 0th row 5th column you are having an element 7. So in this way the triplet representation of sparse matrix is being generated. This triplet representation, as it is going to store only the non-zero terms, it will be space efficient as well as it is helpful for performing operations also. The common operations which are being performed on the matrix, among them includes the transpose operation. Now let's see what do you mean by a transpose operation. A transpose is interchange of rows and columns. The element at the position ij will be at position ji in the transposed matrix. In the triplet representation also, when we have to perform the transpose operation, we have to interchange the rows and columns. But the thing is that we have to maintain the rows in the sorted order. As you will be observing in the triplet representation, there is a row measure format. This row measure format is being maintained. Similarly, when the transpose operation will be performed, we also have to maintain this row measure format. So let's see how do we maintain this row measure format and perform the simple transpose of sparse matrix. For that, we follow a simple technique. We check the column and insert it as in the row in the correct position. So all the operations will be, or the checking will be on the basis of the column, and while inserting it as a row, we are going to perform the exchange of row and column, and the element will be maintained as it is in the transposed form. So let's see the simple transpose along with the pseudocode and the example. Here you will be observing that MAT refers to the triplet representation of the sparse matrix and TMAT refers to the transpose of the sparse matrix. The 0th row is reserved for storing the total number of rows, total number of columns and the number of non-zero terms. In the transposed form, you will be observing the number of columns has been changed to number of rows and the number of rows has been changed to number of columns, and the number of non-zero terms are maintained as it is. Now let's see how this is being performed. A variable k is being initialized to 1 and a loop which starts from 0 up to the total number of columns. MAT 01 refers to the number of columns. So here in this case it is 6. So starting from 0, while I is less than 6, this particular operation will be performed. J is initialized to 1 and J goes up to MAT of 02. 02 refers to the number of non-zero terms. Means starting from row 1 up to the total number of non-zero terms, this particular operation will be performed. That means for all the non-zero terms, this operation will be performed. It is going to check the value of I with MAT of Ji, J1. So I here refers to 0. So it is going to go from 0 to 6 for all columns. It is going to check which column is being present. So initially I is 0. So it is going to check for all the 0 column entries which are going to be transposed into row into the transposed matrix. So all the 0 column entries will be observed and they will be transformed as a row. So you are going to compare I with mat of J1. J1, J is starting from 1, so it is going to refer to the column values. So you apply the check on the column values and check for the occurrences of 0th column, then 1 column, then 2 column, 3 column, and correspondingly up to the total number of columns that are present. And in each of these cases, you are going to check for that corresponding column value, transfer it into the transposed matrix at the position, at its appropriate position. While transferring, you have to exchange the column and the row. The column will become row and the row will become column. So in this case, if you observe, if for I as 0 and if mat of J1 is also 0, you are going to shift that entry, okay, into the transposed matrix at location K. K is going to start from 1, and as the 0th row is kept reserved for the total number of rows and total number of columns. So this is going to proceed for all the terms. So first the 0th column will be searched, it will be transferred. Then column 1 will be searched, it will be transferred. Column 2 will be searched, it will be transferred. And while transferring, there will be exchange of rows and column values. The non-zero term will be maintained as it is. Then you observe that there is no column referring to 3. Next, 4 will be checked and it will be transferred. And 5 will be checked and it will be transferred. So in this way, you perform a simple transpose in which you are focusing on the column values, checking the column values right from 0 up to the total number of columns, and then you are transferring them into the transposed matrix one by one, and while transferring, you are exchanging the rows and columns. This is going to generate the simple transpose of sparse matrix. The limitations of simple transpose is that if the computing time of simple transpose is terms into columns times, and without the triplet representation, the original matrix transpose requires rows into column times. Now, if the terms in the sparse matrix is of the order rows into columns, then the triplet form will require big O of rows into columns square time, which is worse than the regular representation. Hence, for better efficiency of triplet representation, fast transpose algorithm is used. The time complexity of fast transpose algorithm is big O of terms plus column times. So, the simple transpose has big O of terms into columns times, which will be reduced to big O of terms plus column times. These are the references being used for the preparation of this video. Thank you.